Happy Thursday. Sorry I missed you Tuesday. I'm still not 100% here. I'm on Dayquil, which makes me super loopy. So if I'm not making a lot of sense, just holler at me. I'm knocking upside the head. I wanted to post a lab for you. I was going to do it, and then I took my meds, and it just knocked me out, and I fell asleep. And then by the time I woke up in the afternoon, I didn't know what day it was anymore, and I forgot. So eventually we'll do a lab next week. So have the week to catch up. Should be fine here. And so we got to talk about maps and hash tables today. The skip list just gets a mention. Go look it up in the book. You may or may not pick it up in the next class here. That one's not quite as interesting. It's just here's a fun way of storing some data here. But we'll build our own map and we'll use a hash table to do it to get some really good performance. So we'll have a little bit of fun with that today. Fire a pie chart here. Oh. All right, so make a new project. I gotta go find my whole path and everything here. That's fun. Documents. GitHub 2001. Oh, good. Okay, I have it here. Let's make our welcome script, and we'll call this, what is this, week 11? Maps here. We got Python. Cool. So a map is just a dictionary. We've used dictionaries before. We've done a whole lot with it here. We're going to look behind the scenes, how it works, and what kind of performance we get with it, which is really cool. So if you remember with dictionaries, there's no order here. It's just here's key value pairs, and you need unique keys. And we're going to see why some of those reasons are the way that they are here as we go. So just like a fun, interesting thing here. If we were to write a class for, oh, my Zoom's not here. Goodness. Let me go to my settings. I just had to reinstall everything on this laptop here, sorry. Zoom, and it's slow. You want Zoom with the mouse. Editor? Here's my advanced settings. It shows an indicator, appearance. Key maps. Is that it? Zoom? Yes. Zoom the IDE. Let's add a mouse shortcut. Full wheel down. Is that it? Nope. That's not it. Hang on. I'm sorry. I'm super out of it right now. Move. This one here. Zoom in and zoom out. So let's add a mouse shortcut for zoom in. We'll go up and zoom out. Go down. Hopefully that makes that a little bit nicer. Whoa. Oh, goodness. Okay. Well, it works. But the whole thing zooms. That's not what I wanted. Guys, should we just go home? It's not the whole IDE. No. Move that one. Move that one. I just want the font, right? I want... Change the font size. This is it. Thank you. That's the one I wanted. Now I can zoom in and out. Okay. Sorry. So if we write a class for, I don't know, here's weather, because weather seems to be fun right now, and we have some in it here. And we take, I don't know, here's like the temp, and here's the, what is it called if it's rainy or sunny or? Precipitation? Yeah, sure. Oh, I can't even spell that right now. Precipitation. Sure. All right. Self.temp is the temp, and self.precipitation is the precipitation here. Cool. So we got a class. Right? Now, if I want to make a dictionary here, so we'll make a weather here. So here's today is a weather, and we'll say it's, I don't know, like 40 degrees and rainy here. If I want to make a dictionary of, here's like a weather history or something, I don't know. That's kind of silly, but that's fine. Weather history is a dictionary, and the key is today, and the associated value is, I don't know, gross or something. I don't know if we want to track this and how we feel about it here. Here's weather feelings, right? And we give it a run. It works. Okay. Now, if we were to make, say, here's like a list of, I don't know, here's temps or something. It's just a list of 40 and 30, 45, and 50 or something. And we take our weather feelings and we add a key of our temps. We associate a value of, that's also cold. We give that a run. Now we get a message here. This one says unhashable type list. You can't use a key that isn't hashable. And that's our new technical term for the day. We love our technical terms. So a hash is a quick way to get a one-way value out of something here. So hashing is used not necessarily in encryption, but in security. You can do a one-way hash. The idea is you don't go back. It's a one direction here. So a lot of times we'll use hashes for passwords and things. You never want to store someone's actual password. You want to store the hash of their password, because no one likes it if you get hacked into and all of your passwords are given out in plain text. That's just bad form here. And generally people feel bad about that here, although I guess we're kind of numb to it now. So the hash for a list doesn't work, but there's a hash function. You can give it some sort of object here, so we can hash our weather, today, right? Hash today, and let's print that out. So somehow our class is hashable here, right off the bat here. Let me just comment that out. Don't need that one here. So the hash is some number here, and if we run it again, that's 111857. It's not the same number every time here. So, and if we were to make another weather here, exactly the same here, we'll just say here's another, and we print the hash of another, here we should get a different value. Close, but different, right? And if we're to say, I don't know, third equals today here, and we print a hash of third, now we get, these two have the same value here. They have the same hash here. And if we go and look at, say, well, let's print today.temp, and then we'll print third.temp, and then we'll say, hey, today.temp is, well, amazing, it warmed up here, and then we'll print to both again here as we go. So we're going to see, hey, they were at 40, but now that I changed today's temp, it also changed third's temp, right? So when we said, hey, today, or third equals today, we didn't get a new object created in memory. I now have two variables that point to the same weather stored somewhere in memory. And this is a shallow copy. This is one of the problems we run into when we make objects equal other objects. We ran into this when we were solving one of the projects, right, where you had a copy of a list, I think. I said, hey, this list equals another list, and I had to debug that one. So we run into problems when objects equal another, but we didn't make new ones. So what this hash is essentially giving you is a hash of the memory address here. So in Python, there's a hash function of the base object class that everything inherits from. So, we don't necessarily have to be explicit about it, but everything gets something from object. That's why you can say today dot, and you can see, hey, there's something here from object, right? You can see the class, you can see all these other things that come from object here. So you get some default functions here. So under hash, that's the special function that's run when you ask for the hash of something here, and that's defined in the object class. So all objects are hashable. Now, to make a good hash, we need to be able to get a unique value for our object. Now, hashes sometimes work, but they don't always make a lot of sense. So what's going to happen here is if I make two different weathers that are identical here, if we say they should be equivalent, they should be equal to each other, then they should have the same hash. So the problem is today and another don't have the same hash value. But if we were to say, hey, these two should equal each other, right? If you've got the same temperature, the same precipitation, let's say they're equal. I need to make sure they have the same hash. So we start to run into problems when we define an equals function that takes another. So we're going to return self.temp equals other.temp and self.precipitation equals other.precipitation. Precipitation. Come on, type ahead. Help me out here, right? So if we want to say, hey, they should be equal to each other if they have the same values here. I don't think we need the parentheses there, right? We did need the parentheses, just so we didn't have to add in something here. Sure. But now we get unhashable type weather. It hashed just a minute ago. So Python behind the scenes is saying, if you have the default implementation for equals and hash, you're okay. As soon as we change the implementation for equals, we can't use it in the dictionary without also adding an implementation for hash. Because if we're saying these two should be equal, we need to go make sure that they have the same hash. Otherwise, you can't use it in a dictionary because dictionaries use this hashing thing behind the scenes. It's really neat and fancy. We'll take a look at that, how that all works. So as soon as we add this in here, so I'm adding equals, you can't use it in a dictionary without adding hash. Is that a helpful note there? If I can spell dictionary correctly. I can't spell anyway, but it's even worse when I'm on cold meds. So we can go add in a hash here. So a hash should return an integer value here. Now, technically we can say return 0 here. This is okay, but really bad here. Please don't do this here. It's okay. It will fit, and now it's hashable, and now we can do this sort of thing. We can use it in the dictionary here, and now we get back 0 on all of them. This is bad here. So what we want hash to be is a repeatable result based on our object here. Now, we run into some problems here because what needs to happen with hash is that the hash value should be immutable. So even if something changes in the attributes, I should still generate the same hash. Because it is when I put something in a dictionary, if that's the key, I need that hash value to not change. Otherwise, we won't be able to find it in the dictionary later. It'll cause all sorts of weird problems here. So if we just say, hey, let's return the self.temp here for my hash. Let's add that in, return 0 here. So if we return the temperature, it's going to work for me now, right? Because I get the temperature back for these hash values here. Sure, I can get those ones out. But now if I want to go change something in my dictionary here, where we added today, now if I go and say I want to print the weather feelings key of today, right? I'll get the associated value of gross. This should work here. We'll get gross back out. But now if I go and change today, so if I say today.temp is 50, and I go print the feelings again here, now we get a key error because we changed the value that's used to generate the hash, and now we can't find it. So behind the scenes, dictionaries are using that hash value to find where this thing is. And if that is not immutable, if that changes on you, now it's not workable. We can't do this anymore. So you got to be careful with what you use as hash values for classes here. If it's something that changes, we can't use it if you want it to be a key. So if you add these implementations, we're going to run into trouble. So you have to be careful. Use something that's immutable or it won't work. Immutable. Did I spell it wrong? Thank you for spell checking me. Immutable. I thought I spelled it right. That's okay. So now it breaks here because it changes the location. So again, 0 wasn't great, but at least it stayed the same. But now all of them hashed the same one. So that runs into trouble here. So, excuse me. Let's look at building our own dictionary, our own map here. And we'll see why this works the way that it does here. Okay, so let me go add a new file. Here's our own, I need to use our own name here. Oh, goodness, I don't want to call it, I think I can call it map, right? Because it's not a dictionary. So class, yeah, sure. We'll have a class for map here. Now, map is going to store keys and associated values, right? So we're going to define our init here. To store them, what we're going to do is we're going to use a bunch of buckets here. And there's lots of different ways to go about this. The book takes you through 3 bad ways before it shows you the good way. and it says, hey, this is bad because it's slow for this reason. Like, I could make a list of these things here. Motion sensor light's fantastic. I could make a list of them and I could put one, but then I'd have to go, hey, do I have this key? I'd have to look at all the items in my list. And you can imagine that's going to be really slow. Anytime you have to do something for n items, we got bad performance, right? O of n performance is slow. Because if I want to have a million things in my map, in my dictionary, I don't want to have to look at all million things to find where this key is, right? We can do better. So what we're going to do is we're going to make a bunch of buckets here. So I'm going to say self._buckets here is a list. And what I want here is I want this to be a certain size. So there's lots of fun math behind it here, but essentially prime numbers are really good here. That's a lot of work here. So it'd be nice if this was prime, but essentially we're just going to fill this up here. I'm going to say, hey, this is a list, and I want these buckets then to be more lists here. So a list of lists, and we'll say for bucket in range. Let's go 11 here because we'll work at the prime number eventually here. We'll say self.buckets, and we want to append another bucket here. So I've got a list of lists. So what we're going to imagine here, let me see if I can get Word going here, is I'm going to drop these things in to my buckets. Come on, Word, work with me. This laptop's slow, so that's why I always use my other one. Where's my draw tools? Oh my goodness, guys. Draw? There's a button for draw. Draw tools. Oh my goodness, drawing. They're turned off. Okay, I'm not going to draw it on this. That's okay. Yeah. We're just going to imagine some buckets here. So what we need to do then when I go and add something here. So this is a define, or I'm sorry, define. It is, oh my goodness, I don't even remember here. Python for adding key value pair. Let's go Google it here. What do we get? Geeks for geeks. Thank you. I don't want the update function. Square braces. Yeah, what's this one here? No, what? No, I want to write it myself. Goodness. This one, right? Write your own. Oh my goodness. Built-in function, custom function. Should have looked at this beforehand. I think it's under key, isn't it? Oh, is it under key? Set item. Here, set item. There we go. Set item. Here, for a given key, for a given value. Okay, so to go and set this item here, we take a key and we take a value. So this gives us that square brace notation. So I can say here's the key of, right? And then we also need to go add the get item here. So what we're going to do is we're going to find what bucket this key belongs in. And this is going to be super fast because no matter how many n items I have, it's still just the hash function here to find the bucket. So we're going to get our, we're going to have a little private like get index here for a given key. Right? So if you give me a key, the index that it belongs in, the bucket index here, we don't even call it get bucket index here, right? Bucket index here. It says, okay, we're going to return the hash of the key modulus the length of self.buckets. Right? So if I have 11 buckets here, whatever your hash value is, mod 11 will give me 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is repeatable no matter how many items I have in constant time. I can add things, I can go find the bucket it should be in here, right? So now I can get which bucket it belongs in with this quick arithmetic here. So to go set the item, I'm going to go find, okay, what bucket index does this belong in? So here's the bucket index, and equals self.get bucket index of the key, right? Then I need to go say, is this key already in the bucket here? Is this key already here, right? Because here's a bunch of things here, because I might get the same hash value for different values here, right? things can have the same hash value, but not be equivalent, not be equals here, because I only have 11 buckets. So if I'm going to add a bunch of things here, eventually I'm going to have more than one thing in my bucket, right? So then for item in the self.buckets at the bucket index here, if the item is equal to the key, no, I need the, it's a list, I need a list of tuples. So I need the key and the associated value here. So I need the item dot key, or no, item 0, right? Because that's another list inside of it, because I have 2 items. It's like a list of list of lists. It gets kind of messy here, but it's okay. We'll figure it out here. So if the first thing equals the key, right, then I'm going to set the item index of 1 equal to the value. Right? If I found the key here in my list of items here, maybe we'll call this pairs, right? How about that? Pairs. Does that make more sense? Here's your key and here's your associated value. So I've got a list here with a list. Inside of that then is the key value pair. Here's the key, here's the value. I'll just store it as another list here. Here's the first thing, here's the second thing. We'll put all those ones in here. So if we found it, great. If then we can, if we found it, we can return. We're done, right? We set the value, game over. If we didn't find it then, right? I've gone through every pair in that bucket and I didn't find it. Well, I'm going to go add a new value there, right? So I'm going to take my buckets here, right? And I'm going to append a new list of key and value, right? If I didn't find it, so this is didn't find the key, right? So this is did find the key, updated the value, right? Because you can say, here's the new value for this given key to go set an item, right? That gives us our dictionary behavior, right? You can either add or update with that same syntax, right? So this is the update. We found it, let's go update. This is the add, right? And then for get item, define get item. Now this is weird, it says item here. This is for like if you give me a key. Again, we're gonna go find the bucket index here and loop through, right? For every pair in there, doing this exact same thing. If we found it now, instead of setting the value, we're gonna return the value. Return that one. So if we find the key, if it matches here, right? Now this is using the equals function. This is why if you define the equals function here, you also have to be able to hash. Because I'm saying, hey, these two have a custom way of checking if they're equals. The object one just says, are they the same memory address? Right? Did you set third equal to today? Yes, well, they're the same memory address, they're the same object. Right? I don't have a copy of it, I have 2 pointers to the same thing. Right? So we're going to use the equals for our key here to get the associated value. And then if we haven't done that, right, I can raise a key error, right, and say, hey, this key wasn't found, right, not found. Right? If you try and get something out of a dictionary that doesn't exist, game over, right? It breaks on you here. Okay, so we use that hashing function here to go get which bucket it belongs in, right? So what's cool, and a little bit of math hand waving here, is we're going to assume that, I believe the technical term is uniform distribution, that when we hash objects, we'll get some sort of good distribution of hash values. Like we saw with the weather, that doesn't always work, because if I don't have a good value to hash off of, that's fun noise. If you don't have a good value to hash off of, well, you've got nothing, right? There's not a good immutable thing to hash off of. They're all going to go in bucket 0. That's not good, and if they're all in bucket 0, our performance is crap. But assuming we have good uniform distribution of hash values, we can get really good performance. So if we think about how fast these things are here, no matter how many n items I have, if we've got good distribution here, it's going to relate to how many items are in each bucket. Wow, this is some weird weather. I'm sorry? I don't know what they're doing here. This is, yes, it must be cleaning the windows, right? Or, I don't know what today. So it's going to start coming down to how many items are in each bucket here, because we are looping through each bucket. So we start looking at, okay, well, if I take, this many items in this bucket here, I'm going to have bad performance. So what we can do then is we can keep ourselves at a given size to say, let me make sure I have enough buckets here so that I never get more than 2 or 3 things in each bucket here. Right? So if I've got 1,000,000 items, if I have 1,000,000 buckets, I probably never have more than 2 or 3 values in the same bucket. So we can increase the number of buckets we have to make sure our performance is good. So what we need to do then is we need a way to resize ourselves here. So we're going to define a resize function here. So to resize, we need to go make more buckets and move everything from old buckets to new buckets. So resizing will be really slow because we have to take all n items and put them in new buckets. Right? This is a n operation, right? Because I've got n things, they all have to move to new buckets. But we don't have to do it very often, and if we take advantage of geometric doubling, on average, we'll still get really good performance, which is really good, right? Most of the time, this will be really fast. So to resize then, I have new buckets, right, equals a list here, right? And then for, I don't know, bucket in range, we want the length of self.buckets. Now, again, going to the like doubled and then the next prime number would be better. I'm feeling really lazy right now. You know, double plus next prime is best or something like that. Thank you for turning the lights on. For now, I'm just going to double it here. So we'll say, hey, let's do this times 2, which is lazy, but again, we don't need the fancy math stuff here. We can come back to that later. Let's take new buckets and we'll append another list. Okay? Now I've got space set up here. I have twice as many buckets here. Now I need to go move all of the old things into the new buckets here. Right? So then now I'm going to loop over every bucket, loop over every value in every bucket, grabbing those key value pairs. Right? So for bucket index in range, the length of self.buckets, right? Now we want for every item in that bucket, right? For every pair in that bucket. Then so for pair in self.buckets at the bucket index, right? Which it might be empty. There might not be anything in here, right? Because maybe some buckets have 3 items, some buckets have no items. However the hashing worked out. Again, we're going to assume we got a good distribution. It's a bit of a hand wave, but if we can get a good distribution, this works out well here. So for every pair in the bucket, I need to get the new index, the new hashed value here. So I can't use my hash function here, right? Because this is the length of my original buckets. Or if we like our function, because we like that here, we should go change buckets first. Right? So let's say, hey, excuse me, make the double-sized buckets here, right? Then I can go through and have my old buckets. This is probably easier here. Then equals self.buckets, right? And I want a copy of this one here, right? Make sure we get a copy of it. Actually, no, this is okay, right? Because we're going to save that one here. Old buckets. Oh my goodness, how do we? I think I need the copy. I'm trying to remember now. So make old buckets as the buckets because I want to keep this one around and not lose it here. Yeah, I can do that. And then my self.buckets here will equal the new buckets, right? Because this will say, okay, now you point to this new location here, but I'll still have old buckets looking at all the old ones here, right? So then I'm going to do this bucket index for range in the old buckets here, old buckets. I'll go, hey, old buckets at the bucket index. Now I can use my hash function here because it's going off the length of the buckets, which has been doubled in size. So I'll get the proper index out of, hey, I've got 22 spaces now, or 44 spaces now, or 88 spaces now, right? Whatever this doubling works out to be here, right? So I'm going to take my self.buckets, and I don't need to see if it already exists here because I know they all started as empty. And I know you only have unique values here. So I can just really quickly say, hey, self-buckets at the index of self.getBucketIndex, given the pair dot first. Oh, this starts, okay, this is getting a little messy here, sorry. This is all right. So pair of 0, right, is the key, right? Get the bucket index here. Given the new length of buckets, which was doubled here, go find the new bucket this thing belongs in here and go append it. So find that one and then append the pair, right? So for every pair that I have, which is a key and a value, go find based on the key where the new bucket is and go put it there, go append it in, right? This is just appending here. And this does it for every value here, for every bucket, for every pair in every bucket. Right? And then this goes and resizes, and then we're done. So this is an O of n operation here, right? O of n operation here, because it has to move n things over, right? Copies from old buckets to new buckets. Right? So it's going to be slow here, but that's okay. Now, if we could track how many items we have here, if we wanted to. I don't know if we do that with dictionaries. Maybe you do here, how many items you have, but it's not that important, right, for our purposes. So we can make buckets, we can resize here. So now the trick is knowing when to resize. And again, there's math around this here. You can go say, hey, maybe 75% full, and I should start resizing to avoid having buckets with multiple items. Or sometimes you say, hey, I can go to 150% full. If I have 11 buckets, I could have 16 items before I need to resize. And there's all sorts of math around that I don't particularly care about here. You can get into that next class here. So at some point we need to resize here. So I guess we need to know how many items we have, because you'll calculate something known as the load factor. Say, how many items do I have compared to how many buckets do I have? Right? How full am I getting here? So we'll track that. We can say self.number of items.
Can you resize from the start to a point?
We could make ourselves bigger. We could say, hey, I want to start at 50 or start at 100, whatever it happens to be. You could pass it in as an optional parameter or something here. For our purposes, we're not going to bother. But yeah, that would give you, hey, I know it's really going to be really big here. So then every time I need to go add an item, so set value, setting doesn't change it here, but if I go and append, right, then this one is going to take my self.number of items plus 1, because I've added a new one here, right? So when I go set something here, we can check, hey, and how far do I want to be with my load factor? So we can just set this real quick as like, here's a load factor. We'll say, I don't know, we'll just say 1. This is not very exciting math here. But if our number of items then equals this, or you could do some like 0.75, that's fine. We'll say, let's be no more than 75% full. So if my self.number of items, right, divided by the length of self.buckets is greater than or equal to self.load factor, then we'll call self.resize. Okay, so if we get more than this load factor, hey, I've got more than 75% full here, let's go resize. Let's make some more room. Again, there's math around what's the optimal place to resize. I don't remember what it is. We could look it up for Python dictionaries. I forget exactly what that happens to be, but the math is not the interesting part here. But on average, because we're doubling, we still get then average performance of 1 average, our amortized average. Because rarely do we have to double, just like our array-based lists, our lists. We only have to double every so often here. So on average, we get good performance. Now for getting a key out, right, how fast is this based on how many n items I have? Do I have to look at n items to find a given key? No, it's going to be constant, because I go get the bucket index, and then assuming we've got good distribution of keys, of hashes here, I'll find it within 1 or 2 or 3, right? Will be pretty good. So the only time this doesn't work is if we give it something that doesn't hash well. If I say, hey, my hash is always 0, well, now I've got a million things in bucket 0 and nothing in my other buckets. And I've done a whole bunch of work here for nothing. But in general, it works really well. So this works out really nice. Here, you get really good performance. Now, we're trading a little bit of memory usage. This is going to use more memory, especially if we've got more buckets than we need. But we've already kind of dealt with that. Right? We looked at our lists here. Hey, they're already bigger than they need to be so that I can get fast appends without having to resize every single time. We don't even trade off a whole lot of memory here. But no matter how many n items I have now, I'm going to get really fast adds and really fast lookups based on keys. But what you don't get, and this is why with dictionaries, order is not maintained. Just because I put this thing in first and put this thing in second, put this thing in third, I don't know what bucket they're like to loop over items here. I'm just going, hey, here's what's in the first bucket, here's what's in the next bucket, here's what's in the next bucket here. So we could go and give you all of these items out here, looping over them like you do with the dictionary. You loop over all your keys. For key and dictionary, we could do the same idea here, but there's no order because we just get them out of our buckets. So that is our basic map here. So let's go try it and see if it works, right? So let's go back to main. Let's see if we can do that here. Let's probably start at the top, right? So let's go import here. From map, import map here, and let's go make a map, equals a map, and I don't know, we'll say map key of Eric equals an A. We can do some grades, right? So map key of Jeb equals a B, and I should be able to go update these things, right? So map key of Jeb will now go update to an A. And then I should be able to print these values back out. Right? Map key of Eric and print map key of Jeb. Oh, is it not? Okay. So I should be able to get out A and A. Yep, so we get A and A back out. So we got the values associated. We were able to successfully update this one here. Right, I guess we can print that before we go change it here. Right, A and B, and then let's go update one to a B and print it back out again. Excuse me, and show that we got the original AB and then we got AA. We were able to update the values here, right? This worked out nice. Now, if I put enough items in, which should resize here, right? We should be able to go and see that it resizes and still get them back out. So I want to go add a bunch of things. I don't know, 4 value and range 10. Let's go take our map key of value, and we'll just associate value. It doesn't really matter here, right? We'll just add a bunch of things, and then can I still get these things back out here after it's resized? I still get them back out after resized. We didn't see resize happen, but we knew because we added more things here, it happened behind the scenes, or we could go watch it in debug mode, right? Put a little breakpoint in your debug, or in your resize here, and run it with debug. Yes, please do that. Oh, I gotta check the wrong boxes. That's fine here. Come on. And it pauses here. Now it's in the resize function. We are successfully resizing, which is cool. So we saw that seem to work for us, which is nice. So that's building our own map using hashing to do that here, which is really fast. Assuming we've done these good things. So again, a big warning, use something that's immutable here that won't change. Otherwise, you won't be able to find it later in the dictionary if you go on and change something. So you can't always hash all of your classes. Not everything is hashable because some classes are just mutable, right? We can change their attributes. It means it's not a good fit to put in a dictionary as a key. It's fine as an associated value, but use something fixed as the key, and that can be your associated value. So again, why would we have a key for weather? It doesn't really make a whole lot of sense. It was just contrived, but we saw that example here. I'm kind of playing with that as we go. All right. And again, skip lists, fun, interesting and all, but just look at it in the book. It's another way of storing information here as you go. There's other ways of building out these hash tables here. I like this idea of doing the buckets. There's other approaches and there's other trade-offs and things. If you want to get super fancy, you can make singly linked lists instead of a Python list, and it performs slightly better. I think the actual Python implementation, I don't know what they actually use here, but lists are easy for us because you can append to them or remove from them. We never even add a delete item, right? It's really easy to delete an item because you can pop it out of a list, right? You don't have to do a whole lot of work with it here as you go. But that's building your own map and hash table as we go here. There's not a whole lot to do for a lab for this one, so that should be fine. We can do our priority queue lab next week when we get to it. I forgot to post it. Again, I fell asleep and had plans. But we did the max priority queue in class. What you're going to do in lab is build a min priority queue. How do we flip around them to make sure we keep the smallest item at the top here? So just a little bit of editing at your part here, just some practice getting in and making it work. And then you'll put stuff in a priority queue, right, and make sure we can get it back out. We get to search trees. We'll look at specifically binary search trees. We looked at binary trees that have the left child and the right child. We'll look at how we can do that. There's lots of fun things you'll get into here in next class and keeping them balanced, right? You don't want to have a tree that's a node on the left, node on the left, node on the left, node on the left, node on the left. Like then you've just got a big chain. You're not going to have any good performance. So smart people have written ways to balance your trees to keep them in a somewhat complete-ish looking form. Not perfect here. It's not a priority queue. It's not that heap structure, so it's not guaranteed, but it keeps it slightly better to get logarithmic performance, which is a lot of fun. We'll spend a little bit of time on sorting and selection. We do the basic easy ones. We did selection sort, we did insertion sort last time. Look at those again, but then we'll look at how we can do a binary search or the binary sort, a binary search in a sorted one here. And then coming up, ethics. I actually have a PowerPoint that I was given by Dr. Ellen Bogan, and it's fine. I don't need to edit it here. That part's not changed. And then we'll do a little ethics lab looking at the moral machine is lots of fun. You get to decide if you're programming a self-driving car, who do you kill? Do you kill the passengers? Do you kill the driver? Which is always fun to look at here. A very entertaining topic here. Then week 15 is just set for the final project work time. So we are working with a partner with this one, right? Because we're working, one of the outcomes is we work as part of a team here. So we will work with a partner. It's not optional this time around here. So you'll have time, and your partner should have this time free because they didn't know I'd be doing the flexible class stuff here. So they can't be like, oh no, I'm busy. They're like, no, you sign up for this class, show up and help. Like do your part here. And then for our finals on the 22nd here, you're presenting your final project here. So the teams will get up and present. Should go pretty well. It's usually in the same room as lectures. We'll double check. They'll release the schedule sometime in April, usually like the week before, but it's probably in here. Yeah. So that's about it for the rest of the class. So we've got just over a month left here. We're winding down on content. Again, we're just going to kind of touch a little bit of these ideas here. We're not going to go super deep on them. You'll pick them up again in 350 as you continue on here. And then we'll start that final project coming up because we've got the last individual project coming up due on Tuesday, right, for our linked objects here coming up Tuesday. So we'll go over the solution to that. And then we can start the final project on the 25th. So you've got about a month to get the final project done with your partner. Should work out pretty well here. It's a big chunk of your grade, but again, it's doable. We'll do it step by step by step, little piece by little piece. Wow, it does not like any of my formats here. I got bad scores on everything here. It's a link. What's bad about my? I don't even understand that. Okay, sure. But that's about it for maps today. Sorry, I'm a little bit fuzzy still here. Hopefully it made a little bit of sense. But again, the textbook is really good. Lots of good information there. But he does it in a little bit of a weird way sometimes with all of his inheritance, and which is good, and that's the right way to do it. But sometimes it makes it harder to understand. So I'm going to skip some of that stuff. And then we skipped over all the slow solutions. Ideally, you can look at it and understand, yeah, that's slow and bad. Let's just not do that instead of spending all the time coding it to look at why it's bad and then throw away that code because that's no fun for anybody here. Okay? All right, well, that's all I got today. Good to see you guys. And on Tuesday then, we'll meet up for lab. We'll do the min priority queue, and then we'll start with the new stuff Tuesday after that, okay? All right, stay warm, enjoy spring. The equinox was this morning at 9:03, I believe, so we're finally getting there to longer days again. All right, thanks, folks.